Brett, you can start.
Cool. Well, thanks everyone. Thanks, Lev, for hosting again, and thanks for taking your time today to come listen to these presentations. They're really worthwhile, I think, for presenting and for just listening and kind of expanding your knowledge and skill set. So today I'm going to talk about bagging and boosting ensemble methods. So we'll kind of talk a little bit about the general concepts behind those, and then kind of the most common implementation is using decision trees as kind of an underlying model that roll up into these ensemble models. And then we'll talk about some of the ways you can implement these types of models in Python, and particularly around regression or numeric prediction. These can also be used for classification problems, but I'm going to mostly focus on the regression type. And then we'll go into kind of a deep dive on an example data set where the model can make prediction errors. The boosting models anyway can make prediction errors, and then what you can do to mitigate those errors and sort of what circumstances would sort of come up that might create those situations. So the first just kind of general concept of bagging and boosting. So we'll start on the left with bagging. It's kind of a democratic sort of idea. So you think, committee, a voting member, Congress, council, board of directors, stuff like that. The concept is you have many individuals that are looking at some data or some problem and kind of independently coming to their own conclusion or vote. And then they all kind of provide their conclusion or vote. And then the ensemble is a combination of all those individual members or voters. So machine learning, you take that concept and you sort of apply it to individual models. And then they kind of independently create their own prediction, their own vote. And then the ensemble is a combination, some kind of aggregation, whether it's majority vote or averaging the individual predictions. And then that's what the final model would predict or output. So on boosting, on the right side, it's kind of similar, but it's the process is much more sequential. And so instead of having these independent entities making predictions or votes, you create one, and then you iterate on top of that one, correcting, excuse me, the previous iteration. Excuse me. And so you're essentially trying to make improvements upon each of the previous models or each of the previous versions outputs. So this is very similar to, like, how science kind of progresses over time. We could sort of, give a theory and people poke holes at it and defend it and say, well, what about this? What about that? And they slowly over time make improvements to that theory. So it's kind of like that kind of a system where you're sort of incrementally making improvements upon the previous version. So in ensemble methods, it's pretty common to use decision trees as the underlying algorithms or models. You can use any model, but these are pretty common to use decision trees. So just a quick little slide deck on sort of decision trees and what they do. You can use it for both classification and regression problems. There are many algorithms out there. They've actually been around for quite a while. So there's a list of a few of the kind of highlighted ones over there on the bottom left. But basically the concept is you take a data set and you try to find the spot where you can make the best split. So you try to find a feature that you split that feature and you go, one of two directions, and then you kind of keep going down that recursively until you reach a leaf node or a terminal node. And then the terminal node has either the classification in that a classification problem or the predicted value in a regression problem. So decision trees, one of the main benefits is that they're pretty intuitive, they're easy to interpret, they're explainable, People like, kind of following them as sort of human decision-making processes. One of the downsides is that they tend to not be super accurate in terms of, particularly for regression problems, just for the simple fact that you're kind of limited to the amount of values you can predict. You can only predict the number of leaves that you have. That's kind of the most values you can actually predict in a regression problem. So if you have a regression problem or a data set that's fairly complicated, you need to make lots of different predictive or values in a whole range of values. They can be a little bit limited in terms of their predictive ability. So that's where this concept of ensemble learning really comes to play. You take this base model like a decision tree, and you try to improve upon its predictive ability. And so the two main ways of doing that for decision trees anyway are random forests and gradient boosting trees. And so random forests would be an example of bagging. Gradient boosted trees would be an example of boosting. And so you could certainly do bagging and boosting with other underlying algorithms or models, but decision trees are fairly common. Just quickly, the term random forest specifically comes from combining decision trees. So obviously, if you take a bunch of trees, that's called a forest. So that's where the forest comes from. Random comes from the fact that to create independence among the trees, you train on random subsets of the data. So that's how you get the term random forest. So kind of putting this all together, you have this base model, decision trees. They tend to be kind of weaker learners in terms of their predictive ability. So how do you make them better or improve upon their ability to make predictions? You apply ensemble methods to them. So bagging, the most common form of bagging is a random forest. You create independent decision trees, typically in parallel, and then they all combine together to make their final vote or prediction. The term bagging actually comes from combining two other words, bootstrap aggregating. So bootstrap is a sampling technique where you sample the data with replacement. So each row, the odds don't change or the probability doesn't change. Every time you select it, it goes back into the data set and can be selected again. So a bootstrap sample of a data set could have individual rows could be selected 0 times, 1 time, 2 times, any number of times. You're pretty unlikely to select every row exactly once. And then in random forest, you can also randomly select features to kind of create the independence between the trees. And then for boosting, for boosting a tree-based model, you're just sequentially building upon each version of the previous tree. So you build the first tree, and then you build the second tree on top of the first tree's errors or residuals, and then you just continue that process over and over, sort of improving upon the previous models, what the previous model wasn't good at. There's another term that's sort of related to ensemble learning. It's called stacking. And so ensembles, typically you'll refer to that when you're combining models of the same kind, like you're combining decision trees or, other individual models of the same type or the same algorithm. Stacking is where you would combine models of different types. So maybe you'd combine predictions from a random forest, a boosted tree, and a linear model, for example. And so that would just be another kind of way to improve predictive ability by combining models of different types to try to get the best possible prediction. And so that kind of leads into this sort of general discussion around what are you using your model for? And this is kind of a continuum, really. It's not really like every algorithm or model falls into one bucket or the other, but you kind of have on one side models that you would use to try to understand or explain the data. Typically, you'd be doing something like a linear regression model, ordinary least squares, generalized linear models, something like that, where you're summarizing a large data set, potentially large data set, into a fairly small number of parameters in the model to help you understand general relationships, versus kind of on the other end of the spectrum where you're building models to try to make predictions for data where you don't know the answer, maybe in some kind of application where you're forecasting the future, or you're predicting something in a transactional system where the output or the outcome hasn't occurred yet, where you're not really as concerned with understanding why the model's doing what it's doing. You're more concerned with the model's ability to make accurate predictions. So in general, ensemble methods like random forests, gradient boosted trees, they kind of fall more towards the algorithms and models that would be used more for predictive ability and performance, and less for sort of understanding the data set and the relationships between the features and the target variable. So in Python, there's actually quite a few options for bagging and boosting for both classification and regression. So I'm going to just focus on the regression stuff. There's pretty much an equivalent version of all these for classification problems. So you can start in scikit-learn, which you would usually do for machine learning in Python. There's a module called Ensemble, and it has, I think, 8 or 10 different regressors for boosting and random forest type regressors, ensemble regressors. The main random forest one is called Random Forest Regressor. And then there's quite a few boosting regressors. Most of them are kind of from, I would say, legacy type algorithms that have been around for a little while. Probably the best one, or the most current one in scikit-learn, is called HIST Gradient Boosting Regressor. Yeah, the HIST is short for histogram based. And that one is really there for speed when you have large-ish or medium to large data sets and you want to train the model much quicker than using gradient boosting regressor. There's also a library called XGBoost, which is separate from scikit-learn, but it has some kind of wrapper methods around its API called XGB regressor and XGB RF regressor, which implement XGBoost version of boosting and random forests in a similar scikit-learn type format and syntax. And these also work well with other scikit-learn stuff like pipelines and tuning processes and stuff like that. So you can almost use them interchangeably with like your other normal ensemble or other regressor type methods. Excuse me. A note here on the histogram based boosting version, you can do that in scikit-learn, and there's also an option in XGBoost to use the histogram based. Basically, the reason why it's faster is it pre-processes the data to create bins, so basically discretizes all your continuous values in the data. And that's really the bottleneck on determining the best split, is trying to find the decimal point where you pick one split or the other. So discretizing them first into essentially a discrete set of integers significantly speeds that process up. Obviously, whenever you discretize a continuous value, you lose some information, so you lose a little bit of accuracy when you do that. But the idea here is that whatever accuracy you lose by discretizing the data into bins, you pick up that back by just training the model a few more iterations. So the net result is you get a faster algorithm, faster model that's equivalently as accurate as you would get with, say, gradient boosting regressor. I'll also just mention quickly, if you haven't used XGBoost library before, maybe you've used scikit-learn but not XGBoost. This guy on YouTube, Rob Mula, has a really awesome tutorial series. There's actually 2 videos on time series forecasting is the problem he's working on, but he's using XGBoost. And each video I think is about 30 minutes long. So it's a really great introductory resource if you're just kind of getting into XGBoost. XGBoost is also available in R. So if you use R, you can use XGBoost over there as well, that same library. So, you've got this data set, let's say, and you want to make predictions with it. That's what you're trying to do. You decide, random forest or boosting is going to be the way to go. Everything looks awesome. What are some potential challenges or problems that you might run into? And one of them that's specific to ensemble methods is this concept of extrapolation. So because those are based on decision trees inherently can't make predictions outside the training data. So neither can these ensemble methods. So random forests are just combining individual predictions from individual decision trees. So it literally can't go outside the bounds of the data set that it trained on, which in some problems could be prohibitive, like time series forecasting. For example, you might have to extract the trend first, model the trend separately, use a boosting or bagging algorithm to model the seasonal variation or whatever other stuff's going on, and then combine the predictions at the end. So that could be a potential way to solve that problem. There is another challenge with boosting problems, and that is the boosting algorithm, based on how big or small the learning rate is, can actually make predictions. It doesn't technically extrapolate, but it can make predictions outside the range of the training data set. And it does this because it essentially oversteps the bounds of the training data set through that learning rate. So every time it makes a new model on top of the previous iteration, the learning rate is the size of the step it takes. And so especially if you get to the boundaries of the data set, like let's say you have a data set that's 0 positive, maybe you're counting the number of days that occur between two things or two events, and it's you can't have less than 0 and it's all positive data. You could potentially have a model that could make negative predictions. And so how would you handle that? What would you do to mitigate that? That's kind of going to be the focus of the next few slides here, and the data set that I'm going to look at. So I've been working on this data set, and I'm not going to go into too much detail on sort of where it comes from and all that stuff, but basically I'm trying to predict the output of a wind farm. So wind farm is a collection of a bunch of individual wind turbines. So these are big, tall wind turbines that have these big blades on them, and they spin and generate electricity as the wind blows. And so we have a historical output from these wind farms over many years of how much they generate in megawatts. And so this example, the histogram, is showing historically kind of the hourly output for a couple of years of one of these wind farms. And it has an interesting distribution. It's not like a nice bell-shaped curve where there's a lot of data in the middle and not very much on the min and the max. It's kind of inverse of that. It's sort of this U-shaped distribution where you have a lot of values near the minimum, which is 0, so it can't go below 0, but it could generate nothing if there's literally no wind. The blades won't spin and the power plant won't produce. Or it could produce, if there's enough wind, a sufficient amount of wind, all the blades will be turning, it'll be spitting out at its maximum capacity. And then you have this trough in the middle of anywhere in between. And so it's kind of this interesting distribution for the target variable. It's essentially bounded on the upper and lower sides. It's bounded by 0 on the bottom and the nameplate of the facility on the top. And our goal, or my goal, is to try to take the weather forecast. So we have an atmospheric weather forecast, and we say, okay, can we train a model that says, given the weather forecast, can you predict how much output's going to have on the wind farm? And the other kind of interesting thing about this is there's kind of this nonlinear relationship between the wind speed and the output of the wind farm. There's a theoretical relationship that exists. It's called the ramp rate of the individual turbines. There is a lot of variation, mostly because we're using forecasted wind speed. And obviously the weather forecast isn't always perfect. It doesn't always turn out to be accurate. So there can be a fair amount of variation when you look at the weather forecast and the actual output that occurred after the fact. So we just kind of, there's also a notebook that we'll post with this that kind of walks through this stuff. excuse me, in more detail. I think Lev will be able to post that along with the slides, so you can dig into the syntax and look at this in more details. But basically, we were just trying to sort of look at how the prediction min and max would vary based on different parameters for each of these algorithms. So first, we start off with random forests, and we just held the number of trees fixed at 500. So that's how many individual decision trees were trained. And then we just varied the max depth of each tree. So we went 1, 2, 4, 8, 16, 32 on the depth. And as expected, the min and max values of the predicted, the models when it was making predictions, didn't go below the minimum and didn't go below above the maximum. This data set scaled to 0, 1 so that it's on a unitless scale, but essentially 1 would be the maximum output of the facility. 0 would be 0 output. So random forest, pretty, much like we expect, stayed within the lines of what we wanted the model to predict. So if we try boosting, we get a little bit different situation. So this is using an XGBoost algorithm, using the XGBoost library. We used the histogram-based method, so it would be a little bit faster. We used again 500 iterations, so similar to the random forest, we used 500, kind of fixing that. And then we used the default objective, which is the squared error. Most of the implementations that you see for regressors will use squared error as the objective function to minimize. So we also used the same kind of values for max depth, but then we tried 3 different learning rates. So the main parameter that's different between, there's quite a few parameters that are different, but the main one is the learning rate in boosting that's not there in random forests. And this is basically the size of the step you take from iteration to iteration. So we kind of did a Goldilocks, small, medium, large learning rate. Typically, you'll see the default in most implementations for a learning rate of 0.1, but that's not always the case. So 0.1 would kind of be a default / medium. 0.01 would be kind of a small learning rate. And then 1.0 would be a larger learning rate. And so what we saw here with this particular data set is smaller learning rates, or a learning rate on the small side. As you got deeper trees, you kind of threatened the min and the max of the data, and you maybe went slightly over, slightly under, but not by too much. You stayed pretty close to the bounds, but you still technically kind of went a little bit over, which would be expected when your learning rate's really small. When the learning rate was kind of the medium default size, we ended up getting, at least early on with not very deep trees, models that kind of made predictions quite a bit below or quite a bit above the min and the max. We didn't quite narrow into those ranges till we got really deep trees. And then obviously, probably you saw this coming, but with a larger learning rate, we really systematically overstepped the min and the max of the data. And so this histogram is showing that last model with a learning rate of 1 and a max depth of 32. And we made quite a few predictions that were, in this case would be considered nonsensical or impossible values, negative output or output above the nameplate of the facility. So let's just pretend this was our model. Obviously, we'd probably pick a better model based on the error, but let's say this was the model we wanted to use. How could we mitigate this? So one option is to change the objective, and you can do this in most of these implementations. They have varying options, but you can usually change either the criterion or the objective function that it's optimizing. So for my particular problem, there's an option to switch this to a logistic optimization, which is basically the same mathematically as a binary classification. So you use the logit function to transform the data from like a 0, 1 to a continuous value, and then you train the model on that, and then you transform back to the probability. So in this example, the data is not technically a 0, 1 output variable or outcome variable, but it is bounded by 0 and the nameplate of the facility, which we can convert to 1. So we can train this model with the objective of a logistic optimization. And those do produce models that stay inside the lines. Essentially, it stays inside, minimum of 0, max of 1. So that would be one potential mitigation. If you had a data set that was maybe bounded on the low side by 0 and wasn't bounded on the high side, you could potentially use, for example, a logistic or a logarithmic transformation like the count Poisson or a Poisson objective to do that. Another option, if you're not really sure about the boundedness of your data set and you don't really know if you've got a minimum or a max, you kind of have to know that to be able to apply those particular transformations. Another option that you have is to use scikit-learn's method called transform target regressor. And this basically takes a baseline regressor, like in our example, the boosting regressor, and applies a transformer on it. And there are a couple of different options. I just picked one. It's called the quantile transformer with a uniform output distribution. You can also pick a normal output distribution. But essentially, you would apply this transformation to the data first, then you train the model on it, and then you inverse that transformation at the end. The nice thing about doing this in a pipeline is that if you have other pipeline steps, like maybe you're pre-processing the features, maybe you're scaling the features, maybe you're imputing missing values, maybe you're applying PCA to the features to reduce the dimensionality, whatever you're doing, it fits nicely in that pipeline. And all the transformations, the actual physical transformation from one scale to the other, all happens under the hood. So when you make predictions, you don't have to worry about inversing whatever transformations you applied to the data to get predictions back on the original scale. So it all kind of takes care of it, which can be a nice benefit if you're actually going to use this model to make predictions in some kind of downstream system. One catch with using this, like any kind of pipeline, you have to be wary of how the parameters get renamed. So if you're doing like a tuning experiment and you want to tune across like the learning rate and the max depth, for example, it might not be called max depth and learning rate. Inside that, it might be called something like transform target regressor __, max depth or whatever. So you can use the get params method once you make that pipeline to say what are the actual parameter names so that you can specify them correctly in other processes. So just to kind of go over the full list of possible mitigation options, when you have a boosting model that you want to use, but it's making some potential or has the potential to make prediction errors, basically make predictions that are outside the range of the data that you trained on. The first thing is, in your tuning process, just try smaller learning rates. Don't use the default, or if you're doing like a tuning experiment, maybe instead of going from, somewhere around the 0.1 range, maybe shift it down a little bit and do some smaller learning rates instead. Or, maybe you pick a model based on its performance and then systematically train the model that you want to use on a slightly smaller learning rate. So you just kind of offset the learning rate a little bit. Smaller learning rates will tend to have fewer of these prediction errors just because of how they step in the process. You can also, if you know the distribution of the target variable really well, and you kind of understand sort of how it's distributed and what kind of transformations make sense, you can manually apply those transformations. You can use log, square root. If you have positive data, if you have some negative data, you can always offset and then apply that. If you're bounded between a min and a max, you can transform that to 0, 1, and then apply some kind of logit or something similar to logit. You can also just take care of that essentially in the regressor potentially. So most of these have objective functions that you can try different things on, especially in XGBoost. There's quite a few options for different objectives that you can train the model on. So you can essentially handle that transformation right there. Or you can use scikit-learn's transform target regressor, put that into a pipeline. It kind of handles the transformation for you, and you don't have to keep track of, oh, I made, change the transformation at the front end, so you got to do the inverse on the back end. So that kind of is a good benefit there. The last thing you can do, which you could do this in conjunction with all the other things, or any of the other things too, is if you know the kind of bounds of the target variable, you can just post-process after you make the predictions, just clip them. So, if your model's making slightly negative predictions and it can't make negative predictions or shouldn't make negative predictions, just put in a simple process that says if it's negative, cut it off and change it to 0. Or if it's slightly bigger than the max value that you want it to predict, just cap it at that max value, kind of in a post-processing type step. So just to wrap up here, we talked about bagging and boosting as kind of general concepts of ensemble methods that you would apply to decision trees to try to improve the predictability of them. So if you're kind of going from a model that you would sort of use for explainability or interpretability to more of a predictive model, or model using it for making predictions, that would kind of be where you'd be using these ensemble methods. The two most common ensembling approaches are random forests, which is an example of bagging, where you're taking a bootstrap sample of the data and you're creating independent sub-models, and then you're aggregating them at the end. There are many versions of boosting algorithms out there. You can certainly get onto scikit-learn ensemble and look through all of them and kind of read up on those. If you just want to start with kind of the one that usually works the best in my experience, it's HISP gradient boosting regressor, or you can use XGBoost library as well. These are generally fast, flexible, and accurate models. In my experience, boosting models almost always are at the top. If I've ever had opportunities to train lots of different algorithms on the same data set, boosting almost always comes out near the top. Random forest is usually pretty close. So they're usually, they have a lot of good things going for them. You can do feature importance with them, especially random forest. It's pretty natural to get feature importance out of random forest. You can actually calculate feature importance directly from XGBoost models for both the boosted model and the random forest version. And then there are other libraries that you can use to kind of extract feature importance, which can be beneficial if your features have different costs associated with gathering and grabbing that information and putting it into a process. Boosting algorithms, especially the modern ones, also support missing values, missing features. So if you have a data set that has potential for missing features, that can be a benefit. But one of the main cons of using ensemble methods is that they do not extrapolate by design. So if your problem, like time series forecasting, long range time series forecasting, you certainly would want to consider, is your time series stationary or not? Is it going to trend beyond the historical data that you have? And if it is, then you definitely need to consider some kind of underlying model that would handle the trends separate from from an ensemble method. And then boosting models can make prediction errors outside the range, particularly for larger learning rates. And so, but even on smallish learning rates, you can technically make predictions that go outside their lines, particularly if you have a lot of data near the min and the max. Most data sets that kind of have that nice bell-shaped curve, you're probably not going to threaten the min and the max all that much with your predictions. But if you had a distribution like the one I talked about today, where you have a lot of data near the min and the max, you might need to take some consideration when you're actually making predictions and how to mitigate those nonsensical predictions in the modeling process or after the fact. So that will wrap it up for me. I'll go ahead and open it up for questions or comments.
Well, Brett, thank you. It was good. And I know you were using all these models for a long time and you tried different variations. And so you have a lot of experience. So what you what you were talking about, it's all experience, experience, experience. But by the way, when you're talking about linear regression, just draw the line through points, and you end up having two parameters, A and B, right? Slope and interface, and the intercept. Can you pop up browser and go to documentation for, let's say, for XGBoost, and just look at all kind of parameters this model allows you to use? Yeah. Well, just the documentation. It just, if you just show the list of like how many parameters are there. Like I don't remember, but there are like maybe 40 or something.
Yeah, there's a few, quite a few, and you know, in my experience, some of these I just kind of leave them as defaults. You know, mostly the learning rate, the depth of the trees, the number of iterations. But yeah, there's tons of you can even do L1, L2 regularization in XGBoost. So yeah, there's tons of parameters that you can play around with. So it's very flexible and highly kind of customizable algorithm. There's even some new features for how to encode categorical features, so you don't have to manually do that or do that in a separate step. Yeah, there's all sorts of stuff. Yeah, so it's a very much a model that you would use more for kind of making predictions as sort of the focal point of the model, as opposed to can we understand what the data is, the relationships in the data.
Yeah. So I think one of the main lessons learned is that you should not go with default parameters. You have to absolutely change them and tune them to your data and explore this, because you can really improve your model if you do that.
Yep, absolutely. Yes. So tuning, parameter tuning is super important. Obviously, just kind of as an initial step, you can use the defaults just to make sure your data is working and your script is working and all that. But once you kind of get all that figured out, looking into the different parameters and seeing how they affect the objective and the training is really important. And I would also just say that anytime you're doing a regression or even a classification problem, but mostly regression, look at that histogram of your data, your target variable, and see what does it look like. It's kind of easy. I fall into the trap sometimes of just assuming that, yeah, I've got a mostly normally distributed data set, and then you get along into it, and then you realize, oh dang, I've got like 80% of my data is within 5% of the minimum. What do I do? So there's definitely there's no substitute for getting to know the data set you're trying to model.
Yeah, and another thing I really like about Ensemble, that they're stable and kind of reliable. Remember, you were running AutoML?
Yeah, right.
And like hundreds of models, maybe, I don't know, 100 or 200 models, and then you look, they're ranked in the quality, and on the top you have boosting.
Yeah, it was boosting with min-max scalar, boosting with this learning rate, boosting with this learning rate. I mean, it was just littered, and then occasionally there'd be a random forest thrown in there, but it was mostly boosting.
So this is definitely one of your like main tools, main weapons.
Yeah,
definitely. Like Swiss knife of machine learning.
Yeah, definitely. Yeah, anytime I have more than a handful of features in the data set, I start with boosting, and if it doesn't work, then I go to something else, but it usually always is sufficient there.
Yeah, and another thing, if your data supports like a regular linear regression, so it's pretty linear, you can see it by eye, then of course it's fine. But the benefit of boosting is that, well, what if things are not linear? Like one of the examples you've shown, it's actually predicted sinusoidal thing.
Yeah, it can definitely handle. I've applied it to pretty good success for cyclic patterns and time series, like complex sort of diurnal and day of the week sort of patterns that exist in high frequency time series. Obviously, the data has to be stationary so that you're not trending up or down out of the historical range, but it does very well without those kinds of relationships and complexity of relationships.
And talking about stability, people use the word regularization because what it means, basically, you want to find some regularity, and you don't want outliers and so on. And trees, ensembles, they allow you to get this stability, which actually is built in. So your life becomes much easier.
Yeah, it is. Yeah, one of the challenges with some other algorithms is that, I mean, most algorithms, you kind of, there's some randomness to each individual model run, but the nice thing about these trees is you get fairly consistent predictions that come out of them for the same, underlying data set. You don't tend to get really squirrely results with the same exact data set, which can sometimes be frustrating.
Yeah. Guys, please ask questions.
Yeah, so I have two questions. First question is, in your example with predicting power with wind speed, would you use the trend there? Would you use like a linear trend first?
Not necessarily, because that data set's fairly stationary. I didn't show it, but I wonder if I have a graph somewhere I can show. Let me just pull up something. This one, yeah, this is just a small snapshot. This third panel is the actual hourly output. It's, it's flat, and you could do this over 2 years and it would just be this, basically oscillating between the min and the max. So there is no real trend, because these wind farms don't typically, it would be, they'd have to like add new turbines to increase the capacity of the wind farm. So that's not something that typically happens a lot. So it's not something like, stocks or that would kind of trend or go up and down. Yeah.
But where you see like more linear response that you would put.
Yes. Yeah, that's right. Yeah. So if you had, like I have another application where we're trying to predict or forecast like total number of customers. And, if you go out 2 years, we're probably going to have more, or less potentially, depending on what the application is, but you may extend past your training data set range. So in that situation, you definitely want to have some kind of, maybe model the trend separate from the variation, the seasonal variation, or whatever else is going on. So maybe use an ensemble method for the seasonal variation, and then use like a linear or something similar, a basic ARIMA model potentially to model the trend or the central tendency of the data set.
Okay.
But yeah, in this particular example, they're pretty stationary time series.
Oh, thanks.
Yep.
The second question is, so you're mostly using XGBoost, right, out of all the libraries?
Yeah.
Have you tried are there any reasons to go to other libraries? Have you tried CatBoost, or are like enough features in XGBoost now?
Yeah, I think there's I haven't tried CatBoost before, so I can't really say if it's better or worse than XGBoost. I have typically used data sets that don't have a lot of categorical features, and so like this data set doesn't have any categorical features. It's just all numeric, weather, like temperature and wind speed and wind direction and stuff like that. So all the features are numerical. So I haven't really tested that capability out. Like if you had a bunch of features that were categorical and you needed to, convert them into a one-hot matrix or whatever, that you could have some benefit on another library. I have, just because of necessity, had to use scikit-learn just because of the environment. If for whatever reason you haven't been able to install a newer version of XGBoost or a sufficient version, then you might have to revert to an old, like for example, I'm trying to deploy some of these models on a Microsoft machine learning server, and so we're in the process of upgrading the server, so eventually we'll have a newer version, but the version we have now doesn't have histogram base, so it's kind of limiting. So you kind of have to work some of those potentially not as latest and greatest versions of these algorithms, depending on the environment you have.
Cool, thanks. I said I have two questions, but I have one more.
Yeah.
So you mostly work with time series problem?
I have been working a lot with time series problems, but they're not, I wouldn't call them autoregressive. So a lot of the models that we've been using aren't kind of, excuse me, building forecasts based on some combination of past values, like a a REMA model, for example. So they've been using technically they're time series data sets, but there's no autoregressiveness. Basically using features that we know in the future, like a weather forecast, or day of the week, hour of the day, day of the year, like that stuff in the future. So you can use a general purpose kind of machine learning algorithm on a data set that just has a bunch of calendar features, for example, as inputs, because you can specify those inputs in the future, or any other information that you can obtain that's ahead of the time point you're in. So it's time series, but it's not like a classical time series application where you're building a autoregressive model that makes predictions based on some combination of past values of the target variable.
So
if that makes sense.
Time series regression, where you predict some other variable based on time series X values.
Yeah, like most of the models I've applied, you're predicting the target variable based on a bunch of external regressors that, for whatever reason, you can obtain those for future time points, as opposed to building a model that would predict the next step based on some function of the last 10 steps or whatever.
So you're using mostly XGBoost and not specific models that know time series that
I've tried what was it, there's Facebook had that algorithm, I think it's called Profit. Yeah, I've tried Profit, and I think you can use I haven't seen in Python, I'm sure there's an implementation for it, but I've seen in R where you can use kind of like a REMA or Profit models and apply boosting to them. So you kind of I don't know, I haven't done enough research to really know exactly how the boosting process works, but if you kind of just look at it at the face value, you can theoretically boost any underlying model. So but yeah, mostly I use these because they're pretty fast, so you can get through like a tuning experiment pretty quickly, and they're fairly easy to deploy and maintain. One of the challenges with like an ARIMA type model is if you're trying to apply that to a like inside of a database, it gets a little bit tricky to maintain that.
Okay. Do you do like a feature importance in your models?
Yeah, I try to, especially if, and that's another good thing about these types of algorithms, is the feature importance is generally just sort of how often each feature gets selected in all the individual trees for splits. So it kind of gives you this sort of ranking of, relative importance. So this, I just threw this little graph in here just for this particular data set. Obviously, wind speed was like by far the most important feature. But there are a few other variables in the data set, like temperature and how far out the forecast was, and what day of the year it was. So there's kind of a seasonal variation that we have, an hour a day, a little bit of a diurnal pattern. But feature importance can be useful. At least I've used it, because sometimes you have, you're sort of getting features from different places. It's not like you always have one sort of place to get all your data. Usually it's like you're getting the weather forecast from there, and you're getting the power output from there, and maybe you're getting something else from somewhere else. And so if you're kind of combining all these different data sets into one, sort of data set that you train on, there might be a cost associated with those different processes, right? It might be pretty easy to get these features from here, but a little bit more costly, time or resources or whatever, to get the features from over there. And so if you do feature importance and you say, well, these features, they're hard to get, or they cost a lot to get, but they're really important, so we need to make sure they're in the model and in the process, versus, you know, hey, actually these features aren't helping much. We probably don't need to go to the full extent of trying to fold them into this whole process. Maybe it's not worth it. So that's mostly what I've used it for.
Oh, cool. Thank you.
Yeah, thanks for the questions.
Yeah, and I want to add, remember when, like a Profit, you actually tried NeuroProfit, right? Which is a deep learning model. And you, like ARIMA, you tried Auto ARIMA, right? And some of the findings were that the boosting algorithms like 50 times faster.
Yeah, it was a lot faster and either comparable or slightly better. So it was like, you know, yeah, it was considerably faster. I think the Auto ARIMA one for one of the data sets, I mean, it took well over an hour on a pretty small data set, like a couple of years of hourly data. It just took forever. And so, yeah, it's there's a lot of benefits to using the ensemble methods for this type of stuff.
You're right. And cat boost algorithm is a good algorithm, but it's kind of strange, right? It's for categorical data. It's for huge number of features, like thousands. It doesn't allow you to build deep trees. Like we tried to go like beyond 10 and like whatever. At 16 it just completely hangs. It doesn't even allow to go that deep. So it has its place, but maybe not for the work which Brett was doing. LightGBM is actually pretty good, but XGBoost is conventional, is everywhere. It's probably like a go-to. Maybe it depends on how much data you have. Again, you have to try, you have to tune, right? There is no like one answer.
Right, for sure.
I'll stop the recording because we're almost like 50 minutes. Okay. Okay, I'm stopping.